First, we're going to iterate over every training instance, x sub n, in the training set. We need to keep account of the total number of instances in the data set, and that's what this variable total does. Next, we'll check to see what the output classification is for this particular instance. And if our output for the current instance is y sub k, then we'll increment a total for that output class, total sub k. Next, we'll iterate over the features in this instance x sub n. And for each feature, we're going to test all of the possible values for that feature. So if it's a feature such as GPA greater than 3.6 or GPA less than 3.6, that has two possible values, greater than or less than. For each of these possible values, we're going to increment a count based on the class that we're in, that's the k, and index of the feature value, this j. So this count sub kj is the count for this class for this value of the feature. At the end of all those loops, we'll compute the conditional probabilities. Once we've done all the counting, we just have to do a single division to say the count for each output class and feature value divided by the total number of items for that class is the conditional probability sub kj. Lastly, outside our loop, we'll compute the probabilities for each output class, the probability for, say, geeks and non-geeks, as the total sub k divided by the total number of instances. To help illustrate this process, let me show you an example. Let's consider this simple data set where we've got 15 total instances, 10 are geek, 5 are non-geek. Well, the probability sub k is 10 out of 15 for geek and 5 out of 15 for non-geek. How do we compute the conditional probabilities? Let's consider that we have three features. The first feature is GPA, whether GPA is greater than 3.6 or less than 3.6. What we see is that the geeks, 8 out of the 10 had a GPA greater than 3.6, and 2 out of the 10 had less than 3.6. Likewise, for the non-geeks, 3 out of 5 of them had a GPA greater than 3.6, and the other 2 had a GPA less than 3.6. We might also consider the kind of eyewear that the geeks have, glasses, contacts, or none. We've got three options this time, but note that everyone has to fit in one of those three classes. Thirdly, we have the feature of the person's feelings on the Lord of the Rings movies, whether they've not seen them or they love them. And you can see the different probabilities for geek and non-geek for each of those different ratings. So these are how you compute the conditional probability sub kj and the probability sub k. This is all we have to do to train our naive Bayesian classifier, is compute these probabilities. Next, we need to consider how do we actually do classification once we've computed that data, once we've trained our model. And this is really quite simple, although perhaps it looks ugly. All we have to do here is compute the probabilities for each output class, y sub k, multiplied by all the conditional probabilities, and find whichever value of y sub k produces the greatest probability. We can consolidate this equation up here into this pi form where we have this repeated product for all the conditional probabilities that we've assumed are independent. So this last line is really the key takeaway for how to do naive Bayesian classification. Let me show you an example of that. Remember, this is this last line. This is the encapsulation of how to do a naive Bayes classification once we have all these values. Let's look at an example. Let's say we want to classify this person who has a GPA of greater than 3.6, wears glasses, and loved The Lord of the Rings. Well, based on the conditional probabilities and probabilities that we computed earlier, how does naive Bayes work on this? Well, applying this formula, in the green we have the probability for geek, and in the blue we have the conditional probability for GPA greater than 3.6, eyeglasses, given that they're a geek, and they love Lord of the Rings, given that they're a geek. When we compute this, we can extract these four values from the table that we computed just a few moments ago, do the math, and we get a number of 0.192. Now let's compute the probability that this person is a non-geek given our data. So this is the same individual, the same values in our input vector. Let's find out what these values are. So we've got the probability of non-geek times the conditional probability for each of these values, given that they're non-geek this time instead of geek as they were in this first part. We look up those values in the table or in our arrays that we've computed algorithmically, do that math, and we get this 0.016 value. What this says is there's a much greater probability that this person is a geek given this input than a non-geek. So we would classify them as a geek because the geek formula returns the greater value. So this is how to do classification with Naïve Bayes. What are the strengths and weaknesses of the Naïve Bayes classifier? First, it's very quick in the training process. We're really just doing some simple arithmetic, some counting, some division. We can train Naïve Bayes quickly. Secondly, Naïve Bayes can work with a small amount of data, which is a great strength. Thirdly, Naïve Bayes works for multi-class classification. So if we have more than 2 options, so if we have computer geek, band geek, math geek, Naïve Bayes can work with those multi-class type of problems. Next, Naïve Bayes is interpretable. That is, the result is a probability, which we can understand, and we can understand why we got it. And lastly, and this perhaps maybe the most important, it's shown itself to be an empirical success. It often works surprisingly well, even though the assumption is naive. In terms of weaknesses, it only works with nominal values, meaning we can't have continuous values. We've always got to have categories. And secondly, it doesn't support regression. It just supports classification. As we sum up, let's consider the representation, evaluation, and optimization for Naïve Bayes. Its representation, as we've seen, is this set of conditional probabilities, and we compute them by multiplying this probability, the probability of y sub k, times the conditional probabilities for each of the feature values for our instance. The evaluation, we would typically evaluate it on accuracy, that is the number of correct over the number of total. How do we optimize Naïve Bayes? Well, this is a tough one. The only way that I can think of is really by getting more data so we have a truer sampling of the distribution of the data. In this lesson, we've looked at the Naïve Bayesian classifier, which is a really important classifier that does surprisingly well despite its simplicity. It works for classification, and it's a type of supervised learning. I'm Keenan Casey for Tuts Plus. Thank you for watching.